Hi everyone, welcome to our research paper presentation. I am author and presenter Mehmet Fatih Özkan. My coder is Professor Yauma. We are from Department of Mechanical Engineering, Texas Tech University, Lubbock, Texas. And the title of our research paper is Fuel-Economical Distributed Model Predictive Control for Heavy-Duty Track Platoon. And this is the outline which I'm going to follow today, starting from motivation, then following with objectives. Then I will start talking about the modeling approach, following with control design. Then I will talk about the results with discussion. Then I will conclude the presentation with conclusions and future work section. And first of all, I would like to start with a brief explanation about the track platooning systems. The track platooning is the linking of two or more tracks in convoy by using the connectivity and automated driving technologies. And the main objectives of track platooning systems are fuel saving, reducing carbon emissions, improving road utilization, and safety. And the controlling platoon is feasible with common formation control strategies. And the main objective of the commonly used control strategies is to maintain constant inter-platoon gap distances or constant time headway between the trucks. However, in transient traffic conditions, these spacing control strategies lead to excessive braking and acceleration maneuvers during the trip, even though small inter-platoon gap distances provide reduced air drag force. These energy inefficient maneuvers cause increasing the fuel consumption for the vehicles. Therefore, these strategies are unsuitable for the realistic transient traffic conditions to achieve significant fuel saving for the track platoon. And the possible solution of this problem is eco-driving strategy. Eco-driving strategies provide fuel-economical speed profiles for the vehicles by utilizing the previous speed information through V2V connectivity. And in our previous work, we developed an eco-driving strategy for the automated vehicles, and we observe more than 40% fuel economy improvement, particularly under transient traffic conditions. And objectives of this study is twofold. First, investigating the potential benefits of integrating eco-driving and platooning strategies to achieve the fuel economical trips. And second one is ensuring the local and steering stability of the heavy-duty platoon in realistic and transient traffic conditions. And here we have twofold contribution. The first one is a fuel-efficient longitudinal control design for the leader truck is developed to improve fuel economy by avoiding energy inefficient maneuvers. The second one is distributed control design for the following trucks is implemented with sufficient conditions to ensure local and steering stability. And moreover, the performance of the proposed control strategy for the track platoon is qualitatively analyzed and compared with a human-driven platoon and a benchmark formation control platoon in the simulation studies. Let's move on to the modeling approach. So in this study, we consider a homogeneous heavy-duty track platoon where the platoon consists of one leader truck and three following trucks, as we can see in figure 1. And the leader truck follows a one human-driven vehicle on the road. And this human-driven vehicle follows a predefined speed profile, which is US06 in our study. And here we consider two different control strategies for the longitudinal control of the track platoon. The first control strategy is eco-driving for the lead truck, which provides a fuel optimal driving during the trip. And the second control strategy is distributed model predictive control design for the following trucks, which aims to regulate the inter-platoon distance gap with a constant distance policy and zero relative speed within the platoon. To sum up, we called our proposed approach as eco-DMPC. So let's move on to the vehicle dynamics model. Here we use nonlinear third order model, which consists of gap distance, speed, and acceleration. And here we consider linearized version of the vehicle acceleration model. Nonlinear version can be seen on the left-hand side. And the leader truck has three system state variables, which are gap distance, speed, and acceleration. And here we use discrete state space model by using the zero order halt approach. And for the following trucks, we have two system error dynamics, which are spacing error and speed error. And we have three system state variables, which are spacing, speed, and speed errors. And the last one is vehicle acceleration. And here we use discrete state space model by using the zero order hold approach. So let's move on to the eco-driving approach. So eco-driving strategy provides a fuel-economical vehicle motion planning for the leader truck. And here we assume the perfect knowledge of the speed preview through V2V connectivity. And this eco-driving strategy is nonlinear model predictive control based integrated with a power-based fuel consumption model. So let's talk about the cost function and constraints. The cost function is accumulated fuel consumption within the prediction horizon. And here we use Virginia Tech comprehensive power-based fuel consumption model. And this fuel consumption model captures the airflow alteration with variable spacing by incorporating a drag coefficient reduction. And besides, we apply the constraints for the states and the control input considering different aspects, such as safety and allowable distance for V2V connectivity, speed limit, and vehicle drivability. And this proposed an NPC design solves a nonlinear problem with the sequential quadratic programming approach. So next one is distributed model predictive control design. Here, a serial DMPC with producer follower communication topology is considered. And we consider the following objectives for designing DMPC strategy for the following tracks in the Platoon. The first one is all the local NPCs should be recursive feasible. And second one is entire system should be asymptotically stable, which says that all the following tracks will reach the equilibrium point over time when the acceleration of the leader track is 0. And the last one is the entire system should be steering stable, which indicates that the peak magnitude of the spacing error should not be amplified through the Platoon. Here we consider the L infinity steering stability. And the cost function consists of stage cost and terminal cost. So let's move on to the more details with cost function and the constraints. So here, again, we have the constraints for the states and the control input. And we impose the constraints to the vehicle acceleration and control input concerning the vehicle drivability. And then we apply the constraints to the spacing error to guarantee the L infinity stability. And in the cost function, the weight of the terminal cost can be found by using the algebraic Riccati equation. And the stage cost weight matrix is the positive definite matrix, as you can see on the left-hand side. And in the previous section, we formulated the NPC as a control strategy for the following tracks in the Platoon. Next, we will derive the feasibility and stability of the proposed DMPC design with the following lemmas and the proofs. So here I will talk about the lemmas and the brief expression of the proofs, and the detailed proof derivations for each lemma can be found in our manuscript. So the first lemma is the DMPC algorithm for the following tracks is recursive feasible if the initial state is feasible and the following states remain in the feasible set. So here, as a proof, we assume that the NPC is initial feasible with respect to the constraints, and there exists an optimal sequence for all the following tracks. And next time interval, the solution is also feasible for the following tracks with the optimal sequence. So therefore, the DMPC algorithm is feasible at all time steps. And the second lemma is that the DMPC algorithm is asymptotically stable if the following track 1 is asymptotically stable and the DMPC algorithm for the following track is recursive feasible. So to prove that the following track 1 in the Platoon is a cost function, and this optimal cost for the following track 1 is a Lyapunov function, which decreases over time. So we satisfy this requirement by detailed expressions, and we found that the following track 1 is asymptotically stable. So if the following track 1 is asymptotically stable, which means that it will not decelerate or accelerate when it reaches equilibrium. So therefore, the remaining following trucks in the platoon will not receive any disturbance from the leader truck, and the following trucks will be asymptotically stable as well. And the last lemma is say that the MPC algorithm for the following truck is string stable when the MPC algorithm is recursive feasible. So if we say that the MPC algorithm is recursive feasible, which means that the state constraint of the spacing error is satisfied at all time steps. So therefore, we can say that L infinity stability is satisfied when time goes to infinity. Let's move on to the results and discussion. We compare our proposed eco-DMPC approach with two baseline methods. The first baseline method is a pure DMPC formation control without eco-driving strategy, where the previously developed DMPC algorithm is adopted for each truck to maintain a constant gap distance and zero speed difference with its predecessor in the platoon. And the second baseline is a human-driven platoon, where the human-operated trucks are modeled by an intelligent driver model. We first evaluate the fuel economy performance of the proposed eco-DMPC design with the baseline strategies. Figure 2 shows the speed, acceleration, and gap distance profiles for the leader truck in the speed plan strategies. As shown in Table 2 and Table 3, the leader truck with the proposed eco-DMPC design performs with roughly 18% better fuel economy compared to the MPC baseline and 9% better fuel economy compared to the IDM baseline. Moreover, each following truck and the overall platoon with the eco-DMPC design shows significantly improved fuel economy compared to the baseline strategies. The fundamental reasons are that the eco-DMPC design better balances its gap distance with a smoother speed profile to minimize fuel consumption by utilizing the preview information compared to the IDM baseline. And the eco-DMPC approach utilizes the gap distance to the preceding transit traffic as a cushion to omit strong speed fluctuations to itself and as well as to the following trucks in the platoon compared to the MPC baseline. And another important performance analysis for the proposed control design is road utilization. According to results in Table 4, eco-DMPC design provides smaller inter-platoon gap distances by utilizing the both eco-driving and platooning strategies compared to IDM baseline. And the MPC baseline has better road utilization compared to the proposed eco-DMPC design and the IDM baseline. The fundamental reason is that the MPC design aims to control the platoon with constant and smaller inter-platoon gap distances during the trip. And in the previous slides, we analyzed the fuel economy and road utilization performance of the proposed eco-DMPC design. And another important aspect for the performance analysis of the proposed design is the local and string stability of the truck platoon. Figure 3 shows the evolution of speed and spacing errors and acceleration of the following trucks. So the results show that the spacing and speed errors and acceleration of the following trucks converge to zero over time when the acceleration of the leader truck is zero, which satisfies the asymptotical stability requirement. Besides, Table 5 shows that the spacing errors decay throughout the platoon, which satisfies the string stability requirement. So as a conclusion, in this study, we designed a fuel-efficient distributed model predictive control design for a homogeneous heavy-duty truck platoon with guaranteed local and string stability. And the proposed control framework consists of an eco-driving strategy for the leader truck and a distributed control strategy for the following trucks in the platoon. And the fuel economy and road utilization comparing studies conducted with formation control and human-driven platoons. And the results show that the proposed strategy has the potential to improve the energy efficiency and road utilization by utilizing the both eco-driving and platoon strategies. Besides, local and string stability of the platoon is satisfied with the sufficient conditions. As a future work, a dedicated control strategy for the truck platoon will be designed to explicitly deal with the disturbance and communication delay under different traffic conditions. So thank you so much for listening us. If you have any questions, we are here to answer.